program of Introduction to Quantum Gravity. Today we will see the covariant approach. Why we shift from one approach to another, I will explain. But before I do that, let me just tell you that the full set of slides I have will be available from tomorrow on. So because at the end of the lectures. But today you have in the web page all the problem set, not just the ones, the first set, second set is also there, and the bibliography, which you can have it in a nicer. Yeah, can you hear me now better? Okay. Okay. Yesterday we have seen approach to quantum gravity following the canonical approach. First, we have the canonical approach for classical gravity, which is due to Arnovit and Desser and Misner. And today we will move to the covariant approach. Why? At the very end of the lecture yesterday, you have seen that the theory requires renormalization, okay? And since the canonical approach is relativistic, so Poincaré invariance is preserved in this approach, is not explicitly shown. So you have to work to see that the theory is relativistic invariant. And after you renormalize, you never are sure that you have preserved this, because you have to add contraterms to the different pieces of the Hamiltonian, and if you don't make it carefully, you are out. So the theory is not anymore relativistic. So in the case of quantum gravity, you might destroy the diff invariance. Even if you keep the constraints, there are many more. But let me just advocate, before we move on, advantage of the canonical formalism. The disadvantage is this one. Renormalization program in the canonical formalism is very awful, okay? It can be done, but you have to be very smart not to miss the main points. But one reason for choosing the canonical formalism is very simple. Try to find the hydrogen spectrum using covariant formalism, path intervals. Please try, okay? And this is the first course of quantum mechanics. I mean, it's not an easy problem even in the canonical formalism. In fact, the first person who solved this problem was Wolfgang Pauli. A few months later that the quantum mechanics was discovered by Heisenberg. And he solved the problem in the matrix language. When he started, the Schrödinger approach was not invented. But he solved the spectrum exactly, because what Heisenberg did was just to solve the harmonic oscillator, which is a much simpler problem. And also in path interval, this can be done very easily, okay? Harmonic oscillator is a quadratic functional integral, and so it can be done. But Pauli did, not in the path interval approach, but in the matrix quantum mechanics approach, and he solved it. So this can be done. But another two reasons why to follow the approach I was mentioning yesterday, in fact, was not the typical, in the quantization program, was not the typical canonical quantization. I used the Schrödinger picture, yeah, using the functional derivatives in all cases, the scalar gauge theory and gravity later on. It was the Schrödinger picture. Yes, it's an authority argument. Last paper by Feynman was approached to gauge theories in the Schrödinger picture. And he claimed in that picture he could prove confinement in 2+1 dimensions. has something to do with the nodes, vanishing points of the ground state function of this theory, and he argued that. So he make a very good speech in Lisbon in a meeting of international physics, and he was advocating for the Schrödinger approach. The inventor of the path integral was advocating for the Schrödinger approach at the end of his life. And the second person who discovered very late the power of the Schrödinger picture, canonical picture for quantum field theory, was Kurt Szymanczyk. I don't know, you are too young, maybe you never heard about Szymanczyk. I mean, there is an equation which is Kalan-Szymanczyk, probably this you know. It was a German physicist, very influential mathematical physicist in the world of particle physics. And, but the main invention was not this Kalan-Szymanczyk. It was just, he was the first guy who allowed to pass from Minkowskian covariant approach to Euclidean covariant approach, which opened the door to the lattice and the Monte Carlo and to the comparison of quantum field theory with statistical mechanics. And so you can put this on the computer. So making diagrams is nice. We know how to do it. There are programs. But if you want to go non-perturbative in these field theories, which is essential for gauge theories, proof confinement, you need to pass to the Euclidean approach, which means time is pure imaginary. And Szymanczyk proved that this can be done. So this was done in the 60s. I think this was one of his main contributions. So, but again, himself in the 80s, so he died very young too, he was rediscovering the Schrödinger canonical picture of quantum mechanics, and he applied that to, of quantum field theory. He applied this to the calculation of Casimir effect and so on. Okay, but now let's move on and pass to the standard covariant approach, which is the most popular one because it's the one where you can make calculations simply, as you know, because you have some background in quantum field theory. But not only that, because it also makes very easy the renormalization program, okay? Keeping the invariance. So let's start again with the scalar field theory in a Minkowskian background. So how you pass from the canonical formally. Canonical formally, everything is working at a fixed time, okay? Later on, I will talk to you about controversial problem when you change time in a non-trivial gravitational background. Keep an eye on this. But here is Minkowski, so no problem with gravitational background. As I said yesterday, there is always a gravitational background. You cannot escape. Even in the Galileo approach to mechanics, the inertia is a gravitational term, okay? But is what you don't see because it's always there. It's the Minkowski, let's say the Euclidean space metric. What you see is the difference when you have an additional external gravitational field, which is the Earth gravitational field. Okay. But here we have the simplest one, which is Minkowski. And to pass to the canonical formalism is quite immediate. You have this as the operator, field operator at fixed time, 0. And then you define the field operator later or former times just by using the Hamiltonian. For that, you have to use the Hamiltonian, which was already described in the canonical formalism. So this operator, no matter if you use the Schrödinger picture or any other picture in canonical formalism, is well defined. It's a Faggion operator. And then if evolution in this, let's say, background is given by exponential of this Hamiltonian in time. So you evolve with minus sign here, with plus sign there, and this is the field operator in the covariant field operator in a space-time. So now we have an operator defined in the whole Minkowski space-time, starting from the canonical formalism. So once you have this, you can try to compute. Okay, you can do the same for all operators we have in the canonical formalism. For instance, you can do the same for the canonical momenta, which you have in this theory, and you use the same formula, and you have a time dependence of this canonical momentum. But then you can compute the commutators of these operators. You know this operator, a fixed time, is the delta function. Is the fundamental rule for quantization. But when you have different times, it's not anymore that. You perform the Fourier transform of the operators, and you end up with this formula. It's telling you that, in general, it's non-vanishing. Momentum and operator, canonical conjugates, at different times do not commute. Of course, if you fix the same time, y naught and x naught, this will give you the delta function. It's the case. Take here the x and y 0, so with p0. So this term vanishes, and here too. But then it's just the normal Fourier transform for a space like E, P special, and x minus y bold phase, like here. The same here. Since you are integrating now in this three-dimensional part, there is only a difference on a sign of P. But because of the invariance of the measure and the reflection, P going to minus P, both integrals give the same result. And the result is a delta function 2 times a delta function, which this 1/2 is the delta function times an I. Yeah, it's an I missing, sorry. In this one should be I. Okay, thank you. I hope in the final version of the notes this will be corrected. So you can compute now, instead of canonical momentum and the field itself. Remember, the field at fixed time was commuting with itself. It's the basic rule of canonical quantization. In fact, in the Redinger picture, the operator was just a multiplication, as in quantum mechanics. Okay, but here, since we have performed this evolution, then we have a different sign here, essentially. And we have a prefactor here, because you can check this formula by taking the derivative, time derivative of this 5. This will give you pi, and derivation of time here gives you a minus sign, plus this prefactor, because it's the P0 component of the momentum here, okay? So, that's right. They do commute if x0 is equal to y0, why not? But they also vanish if the causal difference between 4-dimensional x and 4-dimensional y are space-like. Here I'm taking the convention of Minkowskian metric, which is here, is plus, minus, minus, okay? So this is why space-like vectors are satisfy this inequality. So in that case, this vanishes. So you have a vanishing of the commutator of the field at 2 different space-time points if these space-time points are not connected by a light ray. So you cannot pass information, and then you perform different experiments in one point and in the other, and they should commute, okay? And so this is guaranteed with this prescription for starting from the canonical formalism, you end up with commutation rules in the covariant formalism. Okay, they satisfy for this particular case of free field theory, okay? So you can go further, incorporate the interaction if you have. In field theory, we always have. This is scalar field theory. We have lambda phi 4, we have seen yesterday. So you have a different Hamiltonian because you have this lambda phi 4 here. And then you have to pass to the interaction picture, which is essentially you change the physical states. You evolve your canonical wave function at time t. You evolve with the unperturbed Hamiltonian, as usual. Okay, and you evolve with that in that sense, and you have the interaction pictures for the field. You do the same for the field at operator. Here is just a wave function. Here is the field operator, and the field operator evolves this way, like the Hamiltonian, yeah? But in this case, the interaction picture is obtained from the field in the free case, H naught, and then evolve with H naught too. And the Hamiltonian in the interaction picture is the same idea applied to this interacting perturbation part in the canonical formalism. So in the interaction picture, you have different wave function. This is the physical state, which evolves in time. This is the field operator, but not the field operator of the theory, the field operator in the interaction picture. And this is not the perturbed Hamiltonian, but just the interaction picture of the perturbed Hamiltonian. Okay? So you have to deal with this new picture. You know, there are the Schrödinger picture, the Heisenberg picture, and this picture is in the middle of both. Is Schrödinger picture for H naught and Heisenberg picture and for the interaction. So in the original evolution equation now becomes this in terms of interaction picture. You have the effective Hamiltonian is just the interaction part, I mean, transformed in the picture. And the states are always in the interaction picture, and then you have this simple equation, and you can try to solve this equation by iterating. You start with the state time 0, you apply this Hamiltonian, is the Picard way of solving a first-order differential equation in time. Solution is given by this formula, so this you need to know the total evolution of the physical state in this interaction picture is just with this ut, which is given in terms of the products of the Hamiltonian at different times in the interaction picture. But the remarkable thing is that since you are solving iteratively, the times of each integral are ordered. So this T1 goes, Tn goes from 0 to Tn minus 1, and so on. And finally, you have T2 from 0 to T1, and T1 from 0 to T, the final T. So you have an ordered set of integrals, which you have to sum of all orders. So this is n point, but you can have any arbitrary value of n, so you have a series. And this series normally is convergent in finite dimensions. Here we are in infinite dimensions, so you have to work hard to prove that this series converge, okay? Let's assume that. Well, you can write this in another way, put all the integral intervals the same, the total interval from 0 to t, and define that here in the integral you have only ordered times. It's the same, it's an identity. So this is how this time ordering appears in canonical formalism. Evolution is given in terms of products of Hamiltonian in time ordering. And this Hamiltonian is the lambda phi 4, so it means that here you will have a lot of products of fields at different times. So it means that the basic element you have to know is what is the ordered product of two fields at different times. space-times, x and y. And time order, by definition, is just this. So you have the product in this order, and if they have a reverse order, you have to change the order to put it correctly. And this gives you the Feynman propagator, which is already used by Gabriel yesterday. So you have in this way. I will not put the plus I epsilon, but it's implicitly assumed that there is an ordering problem, which here is explicit in the interpretation of this formula. Okay, this is well known, you already know, but let me just remind you how this works. So finally, to compute this diagram, this perturbation order approach to the scalar theory with lambda phi 4 perturbation, you have to use this rule for the two-point function, which is the Feynman propagator. And then for the rest of the Hamiltonian, lambda phi 4 essentially, this is lambda, you consider that as vertex, because it means the Hamiltonian in the Picard series you have here, each term here has 4 5s. All of them are at the same point x, but if you perform a Fourier transform, they are at different momenta p. So you have this rule, which is for each lambda phi 4 term, you have 4 fields which enter at the same point, and a coefficient in front, which is the coupling of the lambda phi 4 term. So the essential idea, you know that, you have passed these courses. Now you compute the Feynman diagrams for this theory, and you have that those diagrams become divergent if you consider the 4-point function at any order of perturbation theory, and also the 2-point function is also divergent, and also the loop in the vacuum is also quartic divergence. The 2-point function is quadratic divergent, and the 4-point function is logarithmic divergent. So you know how to renormalize, to change, to absorb the divergences into the mass, the wave function, and the lambda phi 4 coupling, and the vacuum energy too. So after you do that, the theory is finite. At any order of perturbation theory, you have to renormalize all the parameters I mentioned. But the essential point is you never lose covariance, because you are always considering lambda phi 4 is covariant. The kinetic term, d mu phi is covariant. If you renormalize the phase, the field 5 keeps covariant. If you shift the vacuum energy, it means the loop diagram is a constant, so nothing changed in the effective bare Lagrangian. So the theory is explicitly covariant. So we keep covariance as the first goal of going to this approach. Let's move to more complex theory, because our aim is to do it for gravity. So the next step is gauge theories. So gauge theories, let me just do it for the abelian case first. But if you have a non-abelian gauge theories, you have a perturbation theory you have to consider. Just pure gauge theories. So the quadratic term of the action can be written in this way. So, you know, it's f mu nu squared. If you expand in terms of derivative, the first term, which is the mu a nu minus delta d nu a mu, is just this expression, okay? Here is the coupling. So, but the problem now is the propagator. Feynman propagator was in the previous case, was the inverse of this operator. But now, this operator is not invertible. It's the difference with the scalar case. First of all, we don't have a mass, which is a problem. Yeah? But what is more important, this term here has a kernel. For instance, if you apply this operator to a field A mu, which is of the form d nu of scalar field, 5, this gives you 0. Because here you get d nu is the box, and then you left the mu, and using this Minkowski here, you have the same thing, so they cancel and gives you 0. So there is a kernel, and we know that this kernel exists because the theory is gauge invariant. So if you do it infinitesimally, you can see that this is these two fields give the same contribution to this term. If you put here normal derivative, see that this symmetry is what is behind the system of a kernel. So we know what does it mean. In the abelian case, or QED, A mu are 4 scalar fields, okay? To fix this ambiguity, we can require transversality. So this is one equation. So we have reduced the degrees of freedom of the theory in 1. We have 3, but we still have 3, okay? How we can go to the, of course, if I impose that, then the kernel of this operator reduced to harmonic functions, okay? Solution of box 5 equal to 0. So we remove a lot of points. But what ends up the counting of this is just use the first equation I mentioned. So in the abelian case, this is nothing but this. Okay, we have an ambiguity which is parameterized by this function, which is arbitrary. So this is one equation, so one parameter. So the final number of, if I consider these two fields as equivalent, this is the definition, but then if I consider A mu and A mu equivalent, the same field, you remember yesterday the projection to the orbit space, we have 2 degrees of freedom, which are the 2 degrees of freedom of the photon. Okay, and this is what is down there in the slide. So you have 2 degrees of freedom, and you can describe this in the covariant formalism just either by requiring these conditions explicitly, or this transversality condition is called a gauge condition, or do something else, which is simpler for perturbation theory, which is instead of constraining the fields to be to satisfy this gauge condition, just add to the action, so change the action in a way that is not anymore gauge invariant by adding this term here, which is essentially if you put a coefficient in front and you tend this coefficient to infinity, this will give a delta function, which is just enforcing the gauge condition. But if you leave it free, or in particular, in this case, if you put 1, it's a choice, you will get the same theory, provided that you include the Faddeev-Popov determinant in this way by introducing some ghost field, which are Faddeev-Popov ghost, C bar and C. You see, these are arbitrary auxiliary fields, principal non-physical, which means that if you compute the integral of these Grassmann variables, it will be the determinant of this operator. This operator, determinant of this operator, is just the Faddeev-Popov determinant, which compensates the effect of the inclusion of this term over there. Okay, this is the usual trick, you pretty sure you will know. So in that case, this change implies that the propagator of gluons become much simpler. Now you write this in terms of derivatives like here. This term goes away. So you have just to invert this operator. And it's very simple. This operator is this in momentum space. The same you can do for that. The quadratic part, which means that you remove the A from here, is just this. Again, you have two free propagators of massless particle. A massive photon with 4 degrees of freedom and a massless ghost with 1 degree of freedom. You can see that in this way, one ghost eats 2 degrees of freedom of the photon field, and you get the same result as doing this calculation in a different gauge. So you can proceed and compute and renormalize the theory and keeping gauge invariance, which now gauge invariance in this approach translates in what is called BRST. BRST is a new symmetry of this gauge-fixed action here, which is modified by this gauge-fixing condition and the associated Faddeev-Popov term here. So the symmetry is given infinitesimally in terms of these equations. First is the infinitesimal variation of the gauge field is the covariant derivative of the gauge field, so they are twisted. The variation of the gauge field itself is 1/2 of the commutator of the gauge field with itself. Remember, they are Grassmann variables, so they don't commute. Okay, they anti-commute. So here you have the variation of the anti-gauge field. The variation of anti-gauge field is just the gauge-fixing condition. So this BRST symmetry is depending on the gauge condition. But the advantage, the bonus of doing this symmetry is that the full action now is invariant under this transformation. You can check that, it's immediate. And you end up that you have dealt with the breaking of gauge invariant just by imposing an extra symmetry, which is this BRST. And you can see that this is 2 degrees of freedom of the photon field or the gauge field. So, and of course, there is a canonical version of this approach, which to some extent tells you that the Hilbert space of states is split in, it has the ghost decoupled from the rest of the degrees of freedom, in the sense that the Hilbert space, the canonical formalism, the product including ghost, is not anymore positive, definite positive. Is non-negative definite, but has a huge kernel. And if you model this Hilbert space by this kernel, which is a lot of degeneracy, which is where the ghost, the BRST exact operators are, you end up with a real Hilbert space of the theory. There is a canonical version of this covariant symmetry, but what is important is that since this symmetry is there, no matter what you do in perturbation theory, if you keep this symmetry, you are safe. So the normalization program has to keep this symmetry. All the contraterms, you have to use regularization schemes which keep this symmetry. For instance, dimensional regularization, or you can use, if you wish, also versions of Pauli-Villars, and all of them keep this symmetry. Okay, this is what happens for non-abelian gauge theories. So what happens in gravity? Now the thing is more complicated. So we jump directly to the covariant formalism because we don't need to repeat all the steps of starting from canonical and going smoothly to the covariant. We start just from the action, which is covariant, and you just quantize as we learned in the previous case. So in this case, you have to do perturbation theory, as in the gauge case. So you assume that you perturb around a fixed background. So let me make a parenthesis here. You know, I mean, I'm pretty sure that you know most of what I'm saying now, but there is a path integral version of all this, which is integrate the Euclidean action, the Minkowskian action, in the space of all fields. You integrate over dA, or you integrate here over all metrics. But there is a huge difference between, as I mentioned yesterday, between gauge theories, gravity, and scalar theories. The main point is that the vacuum in vector-like theories has to be vanishing, because otherwise you have a dipole structure, okay? In the scalar case, you can have a non-trivial expectation of the field, for instance, the Higgs vacuum. And in gravity too, we are living in Minkowski. So the expectation value, you have a background field, you can have a background field, you should. Also the theory, I mean the principle of the theory to some extent forbid that, because all fields are equally, but not all of them. You can have a condensate, which is just the background gauge field, what we feel. For instance, cosmological background field, or Minkowskian background field here. So this is a difference with odd-dimensional helicity and with even-dimensional helicity. This goes on for any higher spin massless field. So everything can be derived from this functional integral approach, but let's not do it. Just concentrate on the action and derive the Feynman rules, which can be derived also for these functional integral methods, okay? But the essential method, you know, is to expand the action in terms of this perturbative field, which is supposed to be small, so weak perturbations here, we do it around Minkowski, so Minkowski is our background. This is what I made the parenthesis to justify why we can expand in a given background, as you do in the standard model. The non-trivial part of the standard model is to prove that there is a Higgs mechanism. This is a non-perturbative effect. You assume that this happens, and then you do this. And here, the same. We assume that there is a background, which is Minkowski, and we see what happens with the quantization of the fluctuations of this Minkowski, assuming that they are small. So you expand the action. The first term of the action is the quadratic part, which has a kernel, which is this second-order differential operator, which is quite involved. And again, it's not invertible. It has a lot of zero modes. Why it has zero modes? Because my action is diff invariant. So at least there are 4 degrees of freedom, because the diffeomorphism infinitesimally is given by a vector field. In 4 dimensions is 4 different degrees of freedom. So this kernel has at least 4 degrees of freedom which are in the kernel. And you can see that essentially these degrees of freedom are the ones associated with this symmetry here. In this case, well, since I'm Minkowski, I can put it normal. This is the effect of diffeomorphism, infinitesimal diffeomorphism, on this background field, and in particular in the fluctuation. So if I put here this term for h mu, no, this will give you 0. This kernel applied to this operator, to this term here, is 0. So this is the kernel of this operator. You learn the kernel because you know the symmetry, diff, okay? It's automatic. Then you have the same counting of degrees of freedom. maybe I will write with a different color. You are going to help me. How many degrees of freedom here you have in the perturbation? This is this operator, okay? This Young tableau. 2 indexes, symmetric, and with repetition. How many? Well, it's a matrix, you see, symmetric. 10, right? So I mentioned yesterday there are 10 degrees of freedom. Einstein jumped from 1 degree of freedom to 10. Okay, 10. So now, you can try to eliminate kernel by requiring, for instance, traceless behavior. So how many equations here you have? 1. So remaining degrees of freedom, 9. I think you have the counts there. So, and then you have the transversality, again, which you can apply here. And these are 4 equations. You end up with 5. 5 is the number of degrees of freedom of a particle of spin 2 with mass. But here we are the graviton, which is massless. So we have to do the same identification. So these two, so you cannot proceed any further by requiring more constraints. You have to mod out, to eliminate degrees of freedom by identify the generated solution. So these two fields are the same. They differ by a diffeomorphism, so they should be the same. So, but how many degrees of freedom enter in this identification? In principle, it seems that 4, but they are not 4 because we require that they are traceless. So, in fact, this field has to satisfy this equation. So there are no 4 vectors, just 3. Degrees of freedom reduced to 2. 3 independent vector fields give me 2. And you can go on. Let me just do as an exercise the case of massless LECT3 particles. These are called tritons, okay? Candidates for dark matter. This is essentially the same idea, so I will go fast. So I have here 3 index, symmetric, okay? So now the diagram is this one. How many degrees of freedom here? Again, the same thing, but now with 3 indexes. Okay, let's go fast, 20. Here you have the traceless condition. How many equations? Here is easy. 4, right? Because 1 index is free. Transversality. Because you know that transversality eliminates diff. How many equations here? It seems that 10, no? Because there are 2 free index. It's like here. But they are not 10 because they are traceless. 9. Number of degrees of freedom of a massive particle of spin 3. Here and here. This is a massive particle of spin 1. 2j plus 1. Okay, 7. And you proceed, and here you identify the fields. Interesting thing is that the field which generates this gauge kind of symmetry is graviton. Remember, here, the field which generates this identification is what you have here, the vector field. And now here, for the spin 3, is just, well, symmetrization of this equation. How many fields you have? In principle, again, it looks like 10, but of course not, because you have a traceless condition, so they are 9, and in fact you have the transversality 2, this equation, not in this index, but in the others, which tells you that, in fact, you have 5, like here. So 7 minus 5 is 2. And you can go on, and you always have 2. So this framework tells you that diff, in this case, here is not if, this symmetry is very large. In fact, it's broken. So this, there is a famous theorem by Weinberg saying that these high helicity theories should not be gauge invariant because they are pathological, but nevertheless, there are theories which are breaks this conformal invariance and are candidates for that matter. Anyhow, but let's come back to the gravity case, which is the one which you have on the screen. So this mechanism of reducing by transversality, traceless, and removing the gauge symmetries, which are, in this case, vector fields of this type, 3, give me just the true degrees of freedom of the graviton 2. But how do you do that in the perturbation theory? Instead of doing this removal by imposing these constraints, which you can do, but it's very, very hard for calculations, you just proceed as in the previous case. You add a gauge fixing term, which is not of that type. This term here is called the Donder gauge. Okay, the Donder gauge is this parenthesis equal to 0. Okay? But then if you add this, I mean, I don't have time to explain why this is convenient, but it's removing all the kernel of the operator you have at once. And if you choose the coefficient on this way, 1, and also you have the Faddeev-Popov counterpart of this gauge fixing, which in this case is this. The final result is that the propagator, Feynman propagator, is very nice. It's just 1 over p squared times some tensorial structure in the numerator. So this is very convenient. It's like the Feynman gauge for gauge theories. And also you have a ghost, which has a normal propagator, which massless, okay? Everything is massless because the theory is gravity. Diff invariance guarantees that you have massless theory. Then you have the vertex and the whole infinite number of terms in this quadratic expansion, which go beyond quadratic terms in the Einstein action. Again, the new theory, which is here, this is the exact Lagrangian, or action, let's say, of the theory, which gauge fixed. And this action has this BRST symmetry. Again, you have ghost, and you have, as in the gauge case, the first part you could guess, because it's just the gauge transformation, but applied to ghost. Instead of having generators of this type, you have ghost. Ghosts are vector-like, in this case. And the rest comes for matching the conditions of the invariance. The ghost now has a derivative inside, a covariant derivative, but again, it's quadratic in ghost. You have two ghosts. One ghost, which is vector-like. The other one is a scalar, okay? No, both of them, sorry. Both of them are vector-like, sorry. It's only one type of ghost. But it's ghost and anti-ghost. But here, all of them are ghost. In the anti-gauge, again, gives you the gauge fixing condition, which is the Donder formula. Okay? And the final result is the whole action is invariant under this BRST. So this saves you in perturbation theory. Now you can go, try to renormalize, and you keep diff invariance. If you can do it. Okay, let's try to do it. Well, problem is that you have a lot of divergences. In this case, they are more dramatic than in the gauge case. And the theory is non-renormalizable by power counting. That's very easy because you have a dimensionful parameter in the theory, which is the Planck mass, which is in front of the Einstein term. And this, when you go higher order, if you absorb in the quadratic term this Planck mass, it means that all higher orders, vertex, they have higher powers of this parameter. So, and they are dimensionful, so you can do nothing. But the good news and surprising news that happened in the 80s was that it was found by Toff and Bellman that the one loop divergences using very clever regularization, dimensional one, was of this type, which in principle means that the Einstein theory is not renormalizable, because if you have to add these contra terms to remove the divergency, this term is not in the Einstein action. This term, neither. None of the two are in Einstein action, so in principle the theory should be not normalized, as you expect by power counting. But what happens is that if you consider a background, which is a solution of Einstein equations, R is 0 and R mu nu Ricci tensor is 0. So these terms in these vacuum solutions of Einstein equation vanish. So maybe the theory makes sense at one loop. Well, you have other things which I will skip because I'm going very slowly. But what happens at two loops, it was proved by Gorov and Sagnotti, although Ilya Shapiro and collaborators had similar results at that time. They found that two-loop divergences can only be removed if you add this control term. Of course, it's diff invariance. As BRST symmetry guarantees that all control terms are diff invariant. This one is diff invariant. But is not in the Einstein Lagrangian, of course, it's cubic. And second, it doesn't vanish. It doesn't vanish because here is the Riemann tensor, which appears in all these three terms. It's not the Ricci tensor, it's not the scalar curvature. So this term doesn't vanish even in vacuum. So that's the end. So you cannot renormalize the Einstein theory. Of course, you can renormalize as an effective theory. You can keep adding. You see this term is suppressed with the mass square of Planck mass. So it's extremely suppressed, but nevertheless, you have an infinite series of divergences, and in principle, this is not the orthodox way of quantizing a theory, because you have no predictions. At any order, you have to add more terms in to change the rules of the game. So the final result is the theory normalizable, but it was then a possible way out is just to modify slightly Einstein theory in a way that you get a normalizable theory. And this was done by Stelle, Ken Stelle, from Imperial College, as Gabriel already mentioned. And the idea of Stelle is the following. Perhaps Einstein theory is not the ultimate theory of gravity, in particular if you want to deal with quantum gravity. So maybe you have some other theory which is also sensible. But the problem is that the Einstein theory with cosmological constant is very successful from the phenomenological viewpoint. For instance, in the late, so they are the basis of the lambda CDM cosmological model, which is the current model of cosmology. And it fits very well with the observational data, which require to be the vacuum energy, just cosmological constant, that some parameter of the Friedman equations is W, it should be exactly -1. And the result is that is -1 with this error, which is very tiny. So the conceptual agreement is that is described by this theory. Good, plus matter and other stuff, but not gravitational terms. So what? The theory is non-normalizable. Of course, we have not included this in the perturbation theory. By the way, one problem. This theory has not Minkowski as background field. So we have to change the background field. You start with de Sitter, and okay, and then there are other problems. Because in de Sitter, you cannot have asymptotically Minkowski. And well, I don't want to enter into that, but there is a problem. So, but anyhow, this more or less tell me that before touching the Einstein equation, I should be very careful because it's quite successful phenomenological. But there is a problem. At very large distance, there are other gravitational phenomena which you expect to complement the standard cosmological model with a description of a phase of the evolution of the universe where you have an inflation, okay, gravitational inflation. And this is connected with some observational data. And the best model who fits this observational data is the Starobinsky model, which can be described in terms of adding this term to the action, which goes beyond Einstein. On the other hand, if you couple gravity to matter, which of course it happens, so matter exists, and if this matter is quantum, you have corrections induced in the gravitational action coming from the loops of this matter, quantum matter. And some of them are of this type. So, and this was in principle the Starobinsky motivation. So why to stick on Einstein equations? Because you know the matter generates this term and others. So take it seriously. If we add this, perhaps this theory can be quantized and renormalizable. But the answer is not. Okay? You go to this theory and try to follow the program I mentioned. Again, you can have BRST and so on, but it doesn't work. The only way, if it works, was the one described by Estelle, who computed one loop. It's just to modify the Einstein equations derived from this, with this Starobinsky term, of course, there, but two more terms. In fact, one more is enough. You have this term alpha, which is a square of Riemann tensor, and this one, which is a square of Ricci tensor. In fact, this term you can forget because there is one topological invariant, which is the Gauss-Bonnet, which is, if you add the Gauss-Bonnet to the action, equation of motion do not change because this is topological. So it's a pure derivative term that, assuming the vanishing at infinity does give any contribution. So you could express then this term in terms of these two. So you can forget about that and replace this by beta prime and gamma prime. So just one more term to the Starobinsky. Let's see how this theory is renormalizable. Again, you compute the propagators. Now life is more involved. So you have, because of these tensorial elements here, you have one helicity 2 part and one helicity 0 part. So on top of that, you have the ghost, okay? The standard Faddeev-Popov ghost. But now, here comes the problem that Gabriel was addressing, that there is a minus sign here, okay? And so this theory introduced more ghosts than the good ones. I call this good ghosts. I split the ghosts in two classes, good ghosts and bad guys. So these one are good ghosts. The Faddeev-Popov, we know they were in Young Mills, they were helping, but there are bad ghosts, okay? We have to skip them. And there are very complicated ways of doing it. But let's just describe the model. And you know, remember, please, alpha, beta, and gamma parameters here. So the mass of these fields, which appear in the propagators, depend on them, okay? For instance, if you put 0, alpha, beta, gamma, 0, you recover Einstein. You can forget also the cosmological constant to skip this problem of Minkowski background, and you end up with this. So what are these projectors? Complicated things, but this can be worked out very easily. So this is more or less what we have in the gauge case. You have a transfer operator, which is delta mu nu minus k mu over k squared. This is the projector of transverse part of spin 1. Then you have scalars, okay? So in that case, it's much simpler. But here you get these 4 momentum terms, which is why you have 4 index here. And, well, that's it. But it's an exercise. In fact, it's one of the exercises of the problem set I was mentioning before, which are on the web. You can download from the web. But then there is a zero helicity sector, which is nicer. Is pieces of here with different coefficients. But the relevant part which multiplies these 2 operators are this, let's say, scalar part that you can split in fractions, in simple fractions. And the first one gives me just one massless particle, which is the real graviton, still survives. So this theory contains Einstein gravity. And also the good ghost of Einstein theory is this one. But apart from that, you have this term, which is a minus sign, and this term, which is a minus sign 2 here. And this means that the interpretation of these 2 extra terms give me that you are describing a theory, putting these 2 together in the standard gravity, of a massless graviton, which is what you want. You want to have gravity. A scalar particle, which has this mass term here, and a ghost particle, which is this one here, and which is a spin 2. It's massive spin 2 particle with the wrong sign. So this is a ghost. But, well, this is what it is. So now we have to face the problem of the higher derivative particles, which is the main subject in the field, and try to skip this probably unitarity lost, or if you want, instabilities. But the point here I would like to make is that there is one particular case. Of course, if you put all beta alpha and gamma 0, the theory reduces to a standard gravity. It's a good check that there are no mistakes, okay? This is. But the other thing which you can check is that there is a particular case. And in fact, these models, these stellar models, have 2 different phases. And they are separated by a condition on alpha, beta, and gamma. Let me just remind you that Gauss-Bonnet term is this combination of the 3 terms, alpha, beta, and gamma, we have in the still Lagrangian. Well, if you replace alpha by 1, you replace beta by -4, and you replace gamma by 1, what happens? And what happens is that these 2 extra particles got an infinite mass. And you are back Einstein theory. Why? Because adding a Gauss-Bonnet term, as I told you, even classically, does not modify motion equations. The Lagrangian is different, but the motion equations are the same, are Einstein equations. So in that case, you should have no ghost. So this is a case, of course, you can put a constant in front, multiplying everything, nothing changed. And so you have a constant, arbitrary constant in this. But what is important is that the masses of these particles goes to infinity. You can check. So the couple not going to zero, because then it will be real particles and Einstein theory will be modified in the infrared, which is very bad. They go to infinity. So they are like Pauli-Villars particles. They are regularized in the theory, but then they go to infinity. So if you are approaching this limit, you put this Gauss field and all this very high energies. You can forget. So this is, I mean, my opinion, the best way of dealing with gravity. Putting these masses so high that do not affect the low energy physics and save the renormalizability of the theory. Okay, this is interesting. But then, if you take the strict limit, in the strict limit, you have infinite. And if you go to the other side of the wall, you have a very pathological theory. Some of this mass becomes complex. Well, pathological, it may be helpful because we were learning that you having complex mass might help. Okay, so there is this transition from one side of the Gauss-Bonnet to the other side. And here, this is one of the sides. Okay, in fact, both, because you can take the coefficients positive or negative, doesn't matter. Okay, this is the main remark, that probably, if you keep close to this limit, you can save the renormalizability and the phenomenology. So, but you can go even further and try to make the theory. The theory is renormalizable. This was shown by Estelle. You can compute the diagrams, because the contra terms are always of these types. These are the logarithmic divergent terms. If you use dimensional regularization, it's the only thing you see. The pole, the massless, the masses of these terms also get renormalized because the coefficients run, right? And they run in different ways. So the masses, which I was describing here, will change with the renormalization group, but the pole of the graviton not. So this is kept. Okay, so that's interesting. But you can go beyond and try to make the theory super-renormalizable. What does it mean, super-renormalizable? A renormalizable theory, as the stellar theory is, you have to compute in perturbation theory 1 loop, 2 loops, 3 loops. At any order, you have to renormalize the coefficients. You cannot escape. You have logs, corrections to any order. So you have to change alpha, beta, and gamma at any order. For instance, you can do it by fine-tuning just to keep the phenomenology at low energies. But if you have a super-normalizable theory, means that you have only to worry about finite order perturbation theory, because after some order, you have no more divergences. You have only, in fact, you can have, in this theory, you can have divergence only at 1 loop. And then higher order are finite corrections to alpha, beta, and gamma, but they are not divergent. So it's nice. Alpha, beta, and gamma, and these theories, unfortunately, have much more, you see, you have much more derivatives, but you can show that the theory only get renormalization in the first terms of this type. For higher orders, you get finite contributions. And you can even, instead of having polynomial a number of extra derivatives in this quadratic gravity, you can have non-local transcendental kernels in each of these quadratic pieces. And again, you have a theory which is finite and higher order perturbation theory. But there is a result. You never get a theory which is finite unless you fine-tune the coefficients. Generically speaking, these theories are always divergent at one loop. Maybe not at higher loops, but at one loop they are. Unless you make tricky arrangement of the, for instance, if you take Gauss-Bonnet in the previous case, you have nothing because you have just Einstein theory at one loop and vacuum solution vanish. But in any case, these theories are simpler for renormalizability, but much more involved for computations. You have much more differential operators and so on. But these are, there is a lot of activity in studying, for instance, how these theories modify cosmological predictions and black holes and so on.
You said if we choose like the Gauss-Bonnet terms, we recover Einstein gravity at one loop, but we normalize.
No. No, Einstein theory is non-renormalizable.
With those terms and those coefficients, I lose the quality that Stell's gravity has that renormalizes. So I shouldn't.
This theory is renormalizable. All these theories are renormalizable, but they are super renormalizable.
Okay, but that's what I didn't understand on your last statement. When I choose
no, here.
As Gauss-Bonnet.
No, here you cannot because I was mentioned. I mean, we have three theories. Stell, this one reduced to Stell when n equal 2, right? So Stell is here. So, but what I said is that you choose alpha, beta, and gamma, and n equal 2. The theory is just Einstein theory. Is not renormalized. Okay? But this is a particular case of n. Here, to get renormalizability, n has to be large enough. For instance, larger than 2. Okay? This is the statement. So not for any n, this theory is super normalizable. N larger than 2.
I was thinking on the previous step, not super renormalizability. Because you said that's good when we have the Gauss-Bonnet term coefficients because the mass goes to infinity.
No, it's good because I check my formulas with Einstein formulas. It's not good for renormalizability. Okay? For renormalizability, you have to be out of this point. But you can be close to that point. The theory is still renormalizable. But the phenomenology at low energy is Einstein. That's the good point.
So I could search for something that's close and gets renormalized.
Yes.
Renormalized constants with a perturbation around Gauss-Bonnet. Something like that.
The problem is that the Einstein term is also renormalized. But okay, if you use dimensional regularization, you have normalizing everything. So let's come back because I'm almost finishing. So these are very popular theories on the market these days, and many others, because here you can have another kernels. Of course, some of these theories have some pathologies. I'm talking generically speaking. As you said, if I take here n equal 2, it's not good, so n has to be large. Here also, this S here is better not to be 1 in some cases. Okay, so it's generically speaking, large S, large N. So what happens with these theories, which are higher derivative theories? As we see here, the smoothing singularities, they give rise to renormalizer theory, but they cannot escape the classical fates which were mentioned by Gabriel. So in particular, these theories suffer from Ostrogradski instabilities. You have quantum ghosts, maybe you lose unitarity or causality, so you have to be careful. And here, this was already mentioned by the Ostrogradski instability for classical mechanics, but these theories in principle suffer from that. And the problem being that you have higher time derivatives. If you lose covariance and you keep just 2 time derivatives in the action, And the space derivatives, you can increase much than 2. You could keep renormalizability and not instability, because the problem with this Ostrogradski thing is that you have accelerations. So more than 2 derivatives, time derivatives. In fact, these slides here capture what Gabriel says, that your action is assuming that they do depend on second derivatives terms. So if you have only this, even if it is a square, which means integrating by part that you have 2 time derivatives, there is no problem. But then you are breaking covariance. So you have to pay a price. You cannot have everything. So but this is the remark down here. And the problem, which is with these super-normalizable theories, is the following. Let me just come back to the simplest case, which is Stelle case. Stelle case has the minimum number of derivatives to make the theory renormalized. It's also very popular. But there is a result here which sometimes is confusing. You can prove that if you have a solution of Einstein equations in vacuum, but solutions of Einstein equations in vacuum are R equals 0 or R mu nu equals 0. Or R mu nu equals 0 is the best equation. If you have that, and you use the Gauss-Bonnet formula here, you can remove this term and replace by those 2 new ones here of this type. And these 2 terms vanish on vacuum solutions. So then it's a claim. If you have a solution of Einstein equation, you have a solution here. But the physical meaning of the solution is very different. For instance, if you have a black hole outside the mass is a vacuum equation. The only reminder of you are trying to find a black hole is that you don't, you put a symmetry, you make a hypothesis that you have a spherical symmetry around one point, and don't you look at Einstein equation at that point. And you have a delta-like behavior, which is just the tensor of the matter in this point. If you do the same here, it will be not a black hole. It will be not a delta function. It will be a box delta function. It's not, mathematically speaking, the solution is the same, but the physical meaning is completely different. It's not the black hole solution. So the Einstein black holes, Einstein equation black holes, are solutions here, but they do not correspond to black holes. Some more singular objects, okay? And the same happens with these higher order theories, because again, if you have, okay, here you cannot replace this term, unless alpha n is equal to 0. If you put alpha n equal to 0, then you are dealing with these 2 terms, and if you have a solution of Einstein equation, which is R mu nu equal to 0, again, this term vanishes, this term vanishes. So you find solution of, this solution is also a solution of this equation when alpha n is equal to 0. But not, you should not claim that this is a black hole of these theories. But it's interesting to connect both Einstein theory and these ones. So these theories have advantages. They smooth singularities, as I said, but they have problems. And we will see next time what are these problems. So let me just flash the problem set for this part. Is, yeah, you can see you have to compute a lot of propagators. And there are indications how to derive it. Okay? If you find the problem, you can try to contact me. My address, email address is maybe you've already found it in the web page, but anyhow, It's quite easy to find today an email address, and especially for a physicist. You don't need to be a hacker. Okay, so I open the questions. Yes? This is perturbation theory. It's not non-perturbative physics. What you are saying, this group of problems are connected with non-perturbative effects in gases. Of course, you have the same problem. And a reason for that is the following. If you have the space of metrics, now you can have the same. Yesterday I mentioned the moduli space of metrics mod diff in 3 dimensions. Yeah, we're in the canonical formalism. But you can do the same for 4 dimensions. You have the metrics here, and then you have the space of moduli. In fact, these tricks is the local version of this modding. No? This is very interesting because you cannot get the real degrees of freedom just by putting constraints, Gribov, and so on. You have at the very end to mod out. There is no other way. Or use Faddeev-Popov. Okay? But few remarks on that. Why there is a problem with copies? Because if you have the space of H mu nu, this is a linear space. So the topology of this space is trivial. It's a vector space. Well, removing some points, I mean, when these metrics are singular and so on. But these points do not generate larger dimension topological problems, okay? So if you are modding by diff, diff has a complicated topology. And then the quotient space has a complicated topology. In fact, it's well known. Well, I mean, there are some technicalities that you have to use instead of C infinite diffeomorphism. You have to work with a kind of Sobolev regularization of metrics and so on. Okay? You cannot work with wild metrics, you know, delta function metrics and so on. You want to have a smooth metrics, and these Sobolev metrics are quite smooth if you take a Sobolev order larger. So this explains why the quotient space has a non-trivial topology. The starting space was trivial, so it means that you cannot get the quotient just by cutting this and taking 1 point in each orbit, because otherwise you will have the same topology as above. So this is a simple topological argument why you should have problems. Okay? So, but then there is another interesting point in what you raise, that how to go beyond perturbation theory. So are these Gribov copies relevant for confinement or not? There are many people working, and especially in the past, on this. But even now, there are some people. It's not clear, because, so maybe I can answer you later, because it takes some time. So if you have any other, it has a question more directly related with the lecture, it will be better to answer this first. Do you have any other question? Yes? You avoid singularities for some choice of the parameters. Otherwise, you have even worse singularities, big crunch. Be careful. No, they do. Even some of them do have two horizons. No, because black holes is in a specific equation. You have a mass, so you have a tensor on the right hand of Einstein equation. You have T mu, no? Which have a rho and a p. So the rho is a delta-like if you want to have a point like a black hole, or if you have a finite volume, you have some. And the solution is the following. It's very simple. So there is one solution of this equation that you call it black hole. In electrodynamics, it's not a black hole, it's a Coulomb charge. I mean, even three-dimensional. But a different thing is this. This should be the black hole for the higher derivative theories, not this. Because solution of that is the same as here. But this is not a black hole, what I'm looking at. I wanted to have a solution of that, and this is much more regular. Oh, much more singular, sorry. This is what I meant in non-relativistic language, okay, in electrodynamics, in electrostatics, let's say. Which one? Okay, I'm cheating there because you can solve this propagator. I put this gauge. You can do also, if you prefer, Donder gauge, which is simpler, okay? If you do Donder gauge, which sometimes is called harmonic gauge, so it's misleading. Some people, usual harmonic gauge is Donder gauge. But what I wrote there is not Donder gauge. It's just both terms of the Donder condition vanish, which is what is in this calculation. In fact, this problem has two sides. One, compute what is written. Second, compute with Donder gauge. And Donder gauge, I already gave the solutions on the slides, but with this condition, not. Okay? So the two first index are from the left, and the D is the propagator. D is expectation value of this operator with the same operator on the right-hand side, alpha and beta. So it's expand the action in terms, was down in the slides, but then you have to use these conditions to simplify this quadratic term. And once it's simplified, you can invert. And what I'm looking for is the inversion of that. It's just linearized until quadratic order. Yes? Yes. No, yes, that's a good point. I haven't looked. I mean, there is a phenomenology quotation of coefficients. There are many choices of coefficients, which perhaps, as you said, one goes to infinity, the other not. But this way of proceeding is not connected with Gauss-Bonnet. In Gauss-Bonnet, both go to infinity at the same time. You mean in GR, in Einstein theory, no? By the way, at the time that Gorov and Sagnotti found this result, I must say that this is brute force. So it's a very hard, I mean, Elia knows very well. It's a long, long calculation. But now, with computers, you can do it in very short time. Okay, this is just a side remark. But historical remark. But here you have the term you were mentioning, yeah? This is what you wanted to know, okay? So these are, the coefficient in front is logarithmic in Planck, in the scale mu, where you fix the coefficient, because in normalization, you have to fix at one scale, the effective value, right? And then it runs logarithmically out of that, okay? So when you have a logarithmic running, it's very hard to decouple from low and high energies because, so in this case, you cannot guarantee. So just by fixing the scale of the running, you can fix the scale from where you have the corrections have phenomenological effects. Below that, you could have Einstein. But one thing which usually happens is the following. Since all these terms have higher derivatives, their effect should be more fundamental at short distance, because they become more relevant at short distance. So for long distance, Einstein term and cosmological constant term are the leading ones, okay? You have Planck scale, okay? In quantum, are relevant beyond Planck scale, which is far. No, you break it forever. I mean, the divergence exists at any scale. You have to fix it at some scale, but the divergence appears at no matter which scale you consider. So, you see, this Gorov-Sagnotti term is highly suppressed with mass, Planck mass. So in principle, to have some relevance, you should consider very short derivative, so very small scales. Otherwise, it's suppressed at long distance. But the divergence appear at any scale, no matter, because they are logarithmic. So this is the most relevant thing of field theory. You cannot fix the behavior of the theory at low scales without renormalizing. By the way, in quantum mechanics, which probably you feel more comfortable because you pass exams and so on, there are also interactions which require renormalization. In quantum mechanics, usually you don't talk about renormalization because you consider potentials like harmonic oscillator, Coulomb, or even higher powers an harmonic oscillator, which is a hard problem, and so on. But there are potentials which are very dangerous. For instance, this potential. which appear in the slides as a correction to Coulomb-Newton's law. I didn't mention because I passed quickly. But this, if you put this potential with a minus sign, so attractive, and some coupling here, you find that you cannot fix the spectrum. And you have to, if you do it in perturbation theory, you have to renormalize. And there you learn what is the meaning of renormalization. In this case, there is a very simple interpretation in terms of boundary conditions at zero distance, so near zero, which again is to fix the scale at a given. The idea is that to try to solve free Hamiltonian approach this, you have a highly oscillating function near zero. Highly oscillating. So you have to fix where to fix the oscillation, not to explode. But anyhow, I don't know if this answers, so it's a general problem. So here you cannot fix the behavior of the model at short distance until you renormalize. In this case, normalization is fixing what happens at given a scale. Short to zero, but not very. No, 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 no. No, no, no. No, the first order in effective field theories is classical field theory. And classically, Einstein, you know what are the solutions. No, no, because this is in the quantum level. At the classical level, there is no divergence. No, no, no. This is what happens. Yeah, but this is one loop. It's quantum. Yes. Yes. You compute that in the higher derivative theory, then this can be handled. Yeah? And then you solve this problem. Once you solve this problem, you look at effective action and try to ask physical questions. In fact, the Wilson approach to normalization groups, which is the most powerful one, is trying to reduce everything to classical field theory. You compute the effective action, and then the correlator is just a classical field calculation. This is the dream of normalization group. You never do that. In effective field theory, you keep quantizing the theory as a field theory till a given scale. It's consistent, but it's not what I meant. I meant just if the behavior of this classical field at three-level order you can trust. And this is what you know, because in cosmology, you never look for one loop. You just look for classical Einstein equation. And if your theory is renormalizable and the effective Lagrangian is the same at low energies, the same one as Einstein, you solve both problems at once. Sorry? This is the title of a paper by Kurt Szymanczyk in the 60s. So, since I mentioned this person at the beginning, so we can end, remember that. But perhaps you can explain what you mean by that. But this is the effective field theory viewpoint. This is the effective potential where you take into account corrections. This is the Newton's law, two masses at the distance r. Okay, this is the infrared cutoff Ilya was mentioning. But here, since you raised the problem, there are some ambiguities which already mean that here these terms can be any, because you have a change of reference frame from change from R to this, which modifies completely. But anyhow, let's forget about this, because the remark by Ilya was about the formalism. So what is the relevance of renormalization in higher derivatives theories at low energies, okay? This is very important in the standard model, because everybody believes that the standard model is non-renormalizable. in a non-perturbative way. In perturbation theory, it was shown by Toff and Bellman long ago. They earned the Nobel Prize thanks to that, so we should not blame them. But in the non-perturbative sense, the only theory which has been shown in 4 dimensions to be fully renormalizable is just QCD, nothing else. Not even quantum electrodynamics. The problem is related to what you are saying in the following sense. Perturbation theory, strictly speaking, is not converging as a series. It's asymptotically good. So you have to decide where you stop, okay? And more or less is to scale you want to describe a perturbation theory. This is what happens with asymptotic series. But this is enough for physics, so and everybody's happy. And we don't call new physics to new orders of perturbation theory. We call new physics to new Lagrangian terms, new fields, new particles. So, thank you.